Okay, my friends, this is Roger, and I am going to peer review MIT's claims about what they have done manipulating magnetism with light, and they also claim to have found a new rare form of matter. Now, let's take and read this down to about this area here. It says that with the help of a playground, they created observing exotic physics. MIT scientists and colleagues have not only found a new way to manipulate magnetism in a material with light, but have also realized a rare form of matter. The former could lead to applications, including computer memory storage, devices that can read or write information in a much faster way, while the later introduces new physics, which is what I have done. Because what they're talking about is electron and a hole. Now listen to this. A solid material, basically anything solid, is composed of different types of elementary particles. They say they're called protons and neutrons. The reason protons and neutrons are protons and neutrons is because they become stable at a certain quantity of electrons. 100% of everything is made of an electron and a hole pair. I will show this. And you can split them. They are light in a double pair. I'll show that. Now, ubiquitous in such materials are quasi particles. The public is less familiar with it. Nobody knows about these, basically. And they're called excitons, they're calling them. It's composed of an electron and a hole, or the space left behind when light is shown on a material, and energy from a photon causes an electron to jump out of its usual position. I say that's not correct at all. Through the mysteries of quantum mechanics, however, the electron and hole are still connected. Yes, that's correct. And can communicate with each other through electrostatic interactions. Now, let's read this one more time because I disagree with what they're saying. Well, I disagree with part of what they're saying. They're saying these include these little quasi-particles, these little tiny particles, and they know they can smash protons into little bits, and they see these things, but they just don't know much about them because they're in a pile of trash. We started from light. We didn't start from gigantic, huge things. So they say these include excitons are composed of an electron and a hole. Absolutely correct. And then they say it's the space left behind when the light is shown on a material. No, that is not correct. Energy from a photon causes an electron to jump out of its usual position. I disagree with that as well. In some degree, this is a little bit nuanced. We have to look at this a little closer, but I am going to show you what they're talking about, the electron and the hole. And they stay together, and they are glued together like they are tight, but you can smash them and split them. Only way I found that is done on a perpetual basis is to use a really tuned Venturi. And that's what I want to talk to these guys about. They're at MIT. They should, and this other guy's down at UT Austin. So anyway, they say that through the mystery of quantum physics, the electron and the hole are still connected. Well, let's look into this right now. Okay, before we go there, I just want to be sure that you understand I am 100% qualified to peer review MIT or anybody that's breathing oxygen. 50 years ago, I knew there was only two dipole-dipole interactions. That was it. There was no such thing as the Bohr model, the Rutherford model. None of those worked. You could not have a gigantic positive core and little tiny electrons. The transfer of energy from light is to atomic vapor. And that's what they're looking at, is atomic vapor, which is light. And light is composed of two electrons. They would call them excitons. Okay, this is absolutely critical you understand. They're talking about protons and neutrons. Those are really big particles. Those are particles that look basically exactly like this. And they're not one big proton and one big neutron. They are all made of electrons, which are made of an electron and a hole. Let's call them excitons. I can call them anything you want, but they are nothing more than what we had always thought was just an electron. But the electron also holds onto a hole. All right, the two of them are glued together. I will show you that, absolutely, no question whatsoever. And the difference between a proton and a neutron is a proton has one less particle. All right, the proton is a charged particle. It wants one more of these. So it will attach to something, just like that. The neutron says, I don't want any more. You come against me and you stay away. I got exactly what I want. I am neutral. A proton says, I want one more. And then another particle, which would be the opposite, would have an extra electron in it. And that would bond differently to something else, because it's instead of positively charged proton, it would be a negatively charged proton, basically. It would have too many electrons. That's when you start going into isotopes. And you put more and more and more electrons into them, or less and less, they become unstable. But they're basically almost that particular element. That's what a nucleus is. It's just a combination of these, call them excitons. And you don't have to have exact correct number of them, because 1839, here, hold on. Here it is right here. This is my theory. Every electron, I call them electrons, they're calling them excitons. That's fine. But they have a dark matter and they have the bright, glowy electron part. They call it an electron and a hole. All right? I call it an electron and a muon, which is the same thing, an electron and a hole, electron, dark matter. Those are the neutrinos. A photon is two of those back to back in bar magnets, because they are nothing but a little tiny particle, and they have a weight. I believe it's 0.000558 or something like that, atomic mass units. But it ends up, you add 1839 of them together, and it equals 1 atomic mass unit, approximately. So you could have 1839, 1840, 1841, 1836, 1852. These are all different numbers, but they're almost the correct number to make the proton. But if it's not the exact correct number, they will become radioactive. They will decay. They will fall apart. They will shed off electrons. They shoot them out of there. And that's what you call, well, that's what you use those for, to pick up that radiation. The particles just spontaneously flying out. And that happens all the time. So there's nothing special there. Things are always moving in nature. And that's why you have to do microsieverts in the background. It's just a standard background radiation. It's just always happening. But anyway, let's get back to the excitons, and I will show you how they manipulated them with light, which we have done long ago. All right, hold on a second. Okay, this is a photon, and I can say that with a certitude because I will show you how I arrived at that with the experiments I did with Rod Warren long ago. This is the dark matter. This, to them, would be the electrons. These would be the holes. They call this now the tetraquark. It's a 4-particle photon, and they've never seen it before because they smash huge particles together, billions. We smash light together, and we force them to concuss and crush the fields and squirt the white, which can concuss and compress. The black cannot. The black is solid, heavy, and it is hard and heavy as hell. These are little puffy things. They don't hardly interact whatsoever. They have almost no mass whatsoever, but they are hotter than hell. And how can I say that? By observing atomic bomb blasts. And I'll show you that. Why is this one glowing and that one's not glowing? That particle's going through the air this way. That is the particles that it's concussing with. These, anytime you push and shove, I call this push to shove. This pushes forward, that shoves back. They will always start to glow on both sides. The bigger, the harder mover one will glow much more than the ones that are stationary and getting impacted into, which is quite obvious now. And I will show you this in some more detail. But don't forget, these are the electrons, these are the holes. That's a tetraquark. Look up all of those, it's all brand new. They're just figuring all this stuff out because they're finally thinking of it a little bit. However, they still have no idea how to do this. They're just seeing these things and finally saying, well, we better say something. Roger's been saying this stuff for 6 years now, stuffing it in our faces, which I did. I even went to the University of Geneva. I took a course there, particle physics, introduced this to them, and they said, ooh, that's pretty interesting, and then they didn't want to have any more to do with it. And Fermilab refuses to discuss it. Everybody does. That's why I'm doing these peer reviews, because the peer review has always been a way to destroy anybody that comes with evidence. Well, I'm coming with evidence, and I'm going to destroy peer review. It's not working. It's just not working. Okay, here's the thing to remember. They're taking two gigantic particles, slamming them head on and seeing all of this debris come out. Because yes, they are separating these particles into these constituent parts, which I will show you. However, they have no clue about them. They just are amazed to see them. This is light, right? That is from a pulsed red laser. Look up light. Light is supposed to be only one speed. We can obviously see that that is not correct. And even though this is not in a not in a vacuum, we're in medium. So that should slow it down, not accelerate it. We accelerate it because we put it through a Venturi. So forget Einstein, forget Hubble, forget all of them. Forget Bohr. 100% is wrong as far as the particle nature, the speed, everything. Now, this is the light, and again, there's a particle back here, but it has the magnetic field around it. So the particle creates a wave that precedes the particle. So you have the particle-wave duality. That's covered now. This is the little pushback particles that are gases in the air, have all the electrons the same as anything else, are made of electrons. So they glow a little bit as these push through to get them the hell out of the way. This goes through, and through a Venturi, it's rocket ships. I mean, it just pulls its little particle right out of there, just identical to a jet fighter exceeding the speed of light, speed of sound. At this point here, they begin to concuss, and they develop and display themselves as what their true nature is these back-to-back particles, which they now call excitons. All right, the black and the white. And I showed you those particles before, attached together, and one can glow more than the other. The white ones can squirt through our Venturi, the black ones cannot. Let me show you that, because that is what CERN and Fermilab wants to see and refuses to discuss for years. That's the muon neutrino, is the black ball. It doesn't change. You see it? There's the black ball. They would call that a sterile muon neutrino. Right there. Normally they were attached together. Remember they said they were linked together, the black and the white one, the electron and the hole? Well, they were. We saw them. No question they were. And now they have, this is not my doodle. This is the doodle from CERN, I believe, or Fermilab. But they want to see this. They want to see that electron shower. There it is. And they want to see the muon go away on its own. And the reason we got it, because we made a Venturi here that was so restrictive that it would only let those little crushy particles through, the white ones. The black ones came up and slammed those white particles through there. And this will do this, just sit there all day and do this. That is nuclear, atomic, subatomic fission and fusion. What is fission? Fission is when particles separate. Fission means the black moved away from the white, which it obviously did. So what do we have here? All we have is the electrons. And what do the electrons do? They burn the hell out of things. I don't know what the temperature is right here, but I can pretty much think that it's got to be extremely high. But it's only for such a brief instant, because now they fuse back together. If we could tap into here, not necessarily for the heat, but for the raw electrons, because here there's just nothing but the electron portion, and that portion electron wants to be back together with that black muon so desperately that it will go through motors and power lights and boats and cars and trains and everything to get to that black side, and to run through motors and make them spin and propellers and jet engines, who knows what, as energy. And that's almost free. We started with a very, very small pulse red laser. And this is literally incredible amounts of energy. You see the increase in energy? Back here, you couldn't even see it. Well, let me get back to where it makes a little more sense. This, what we were using, is CMOS smartphone. It's exactly the same thing they use at CERN and Fermilab. Well, Fermilab, I don't even think knows about this. They're doing all kind of exotic stuff. But you can't hardly see the particle back here because it doesn't have any energetic value here. All we're picking up is radiance and luminosity. And we're seeing the increased value in the pixels. It is very, very exotic, technology, to be perfectly honest with you, but it's within a cell phone. I mean, it's incredible the things we've been getting out of this stuff. And this was years ago, too. They knew this. There's a thing, if you look it up, cosmic ray detectors from smartphones, because they use them for cosmic rays. And the only reason they can see the cosmic rays is because the exact, total, gigantic amounts of energy that they create, which is what you're seeing here. If you can't tell that that's an enormous increase of energy from back here, you're just not a physics thinker. Anytime you see glow and huge radiation like this, that is an enormous increase in energy. So what does that tell me? That tells me if I can harvest that, I should be able to get free energy. And I do have a little device that somewhere around here that I decided might be able to harvest free energy, but I don't have it handy. Oh, well, I'll show it to you later. My point being is that they're looking for the hole and the electron. We had them, and then we split them. That's cold desktop fusion. It's fission, and then they come back and makes a fusion. Single slit. These interference patterns have nothing to do with flappy waves going here and there. Double slit is just not real. Alright, this is the nature of light. It spins. It's a magnetic particle, as I showed you. It has the dark and the white, and it spins, and it's a four-banger. It's a double electron. It spins through here. It creates that drill bit effect. Some spin off to that side, some spin off to this side. Most of them end up going into the middle. That's what light does, spins. See, this is the problem with CERN. They just smash gigantic things together, and they see these little circles coming out of them and all these spinning. We're way down in these particles, and we force them not to smash head on, but to squeeze through the venturi. That's what creates the particle separation. And you can do it on a continuous basis. Right now, when they do their fusion, it lasts a trillionth of a second. They're so excited that they did it for a trillionth of a second. We can do our venturi on just a continuous basis, never stop. Okay, and here's a professor named Gedik. He says the excitons, which is that black and white particle in this material, are rather unique in that they are coupled to magnetism. Well, they are magnetism. They're magnetic particles. And they are coupled to magnetism in the system. It was quite impressive to be able to kick the excitons with light and observe the associated changes in the magnetism. The excitons, light, are little magnetic particles. So they're going to kick because they're kicking another magnetic particles, because everything is made of magnetic particles. So they're just bashing one of these little tiny particles into another. But they are on the extreme subatomic level. They're light. They're not anything to do with solid material. They're light. Or they're strictly electrons. And to me, an electron is just one of those black and white particles. Light is a black and white particle back-to-back, 2-bar magnets, basically. Light is the tiniest particle that there is, and it's made of 2-bar magnets. An electron, to me, they call it an exciton, is 1-bar magnet. Okay, sum it up. Their proton is like this, and they smash it into little bits, and they see these, what they call excitons. My proton is like this, and when we smash it up, all those little bar magnets are the excitons. Light spins. When you look at it from the side, it looks like a wave, but it's a particle, and it creates a wave in front of it as it moves through, so you get the particle-wave duality. Alright, so that explains that. This is the actual physics. There's 1,839 electrons, which I call them excitons. I call them electrons. We'll call them excitons. 1,839 of them make a proton. 1,840 is neutral, makes a neutron. And they seem to be stable at that because they shake and they lock in at those quantities for some reason. I haven't really figured it out, but I think it might have something to do with Schumann resonance or the natural humming vibration of the universe, because there is a natural rhythm to the universe. It just keeps doing that. Now, and it could be that that's what it takes to make them jump into that stability. Now, but no matter what, they are all dipoles. I call it dipole electron flood theory. Maybe they want to call it dipole exciton flood theory. That's okay. It's still my theory, and I still had it 50 years ago. And now I can prove it's true by the things that I just showed you with the experiments in light. Light is the smallest particle there is. There's no question it's a particle. No question it accelerates. No question it can divide. And I need somebody to talk to me. So I just showed you nuclear fusion on a desktop. And we can do that for almost nothing whatsoever. I mean literally a few dollars. And it literally could create free energy, as I showed you with my little device. All we need is to put a little harvester right where that brilliant, brilliant white is. So that's my peer review of these guys, and I sent them both, this Gedik, and I sent the other one, wherever he is, I don't know, down in Texas, and I would like them to respond, because this is my peer review of them. I'm trying to help them. I guess it was this guy here, Baldini, trying to make their work better. Now, I don't know what this playground for observing many-body physics, they just have a little area they can screw around, it looks like. We can do that too. Okay, my friends, I would like my friends from MIT to explain what happens to this house during an atomic bomb blast. Now, this is from atomcentral.com. My contention is that this house will burn and then it will explode. Why does it burn? The light particle, the electron, which can move at the speed of light and has been forced away as the atomic bomb blows all of the light particles first, then the heavy particles follow. But because the electrons completely surround dark matter, they will go first. And they only have the ability to burn things. They don't have the ability to push things around. You watch. You're going to see. This house will combust. It'll literally just turn into flames. And then, boom, everything goes. And then because everything has been pushed away from the dark core, the dark core will say, hey, all you electrons come back. And everything will come backwards. instead of just continuing out, which you would expect. A bomb blows things away. They don't blow them away and bring them back. Well, a nuclear bomb blows them away and brings them back, because what it blew away was its electrons. And then it blew away its, well, first of all, it blew away the white particles. Then it blew away the dark particles that were attached to the white particles. Those are the ones that make this explode. But the core is still back there with a ton of black and very little electrons, which is the white ones. They'll say, hey, come on back here. We need to be complete. I need a black and a white together. Right now, all I got is a black ball, because I sent all you electrons out to burn houses and explode them and all that. Come on back. And phew, they come back. Watch this event unfold. Okay, I'm running this at 25% speed. I mean, 25%. So it's going to take a lot longer to happen than it actually is in real life. But you will absolutely see. This is the initial brilliant glow. And what is happening now? All you have hitting this is those white glowy electrons. These are the things that are coming out first. And they are bright. They are brighter than hell. I mean, they burn. But they do not push. Now watch. 25% speed. Here goes. Boom. Look, watch this. I'm stopping it here and there. It's just burning. It's burning. That didn't go flying. Nothing there moved at all. Every single thing that it hits, especially wires and things like that, they just combust. Watch. You see it burn? Look at it burn. Nothing went flying. It's just like it just turned on fire. Not a single thing has moved. Not one single thing has moved yet. The only thing that's happened is we have a fire. And it burns and burns. And look, it's just billowing out like this thing had just literally spontaneous combustion. But nothing has moved. Look at it. It's just burning. Now watch. Okay, boom. What just happened here? Why did that happen? Explain that to me, MIT. Well, I can explain it. What has happened is the nuclear explosion takes a ball of particles like this, only they are so compacted and so dense with electrons that there is absolutely no extra room. Then they take, that's your heavy-duty stuff, plutonium and uranium and all that really heavy stuff. There's so many particles, they don't even want to be together now. So they want to get apart. But then they take and they surround it with dynamite and all kinds of things to push them together. And when they get in together so tight, they say, no, I can't do this. And all of the white ones go. All of these go first, because they're the ones that are on the outside. They're gone. Then the ones that follow them are complete particles that have both, not only just the electron, but the muon. That's the one that just did this. Because now we got that dark particle, and that sucker is heavy, and it is hard, and it just slammed that house. Now, the takeaway from that is the nuclear core that started the explosion is sitting there with dark matter. Dark matter does not react to magnetic fields, has no reaction whatsoever. It only wants to draw everything back to it. When we exploded it, it just sat there and said, hey, that's no problem for me. I'm dark matter. I don't care about going anywhere other than everybody come back to me. I want to be complete. I have to have one extra white guy for every black guy. And you just sent all the white guys away. And then you sent some more of the white and black guys together away. But I'm still now missing a whole ton of particles, and I want them back. So here it goes, pushing, smashing, destroying. That's the full particle, not just the electron. And boom, look at it. Look at what it does. Look at that. Just phenomenal. What extraordinary amount of vicious energy. And these are complete particles. These are not just the electrons. Now watch what happens. It goes out and then all of a sudden it comes back. Explain that to me at MIT. See it go out, now watch. Boom, it went out. Look, watch, it's turning around, it's coming back. See it? It's coming back this way. Why would that happen? Because the dark core says, I can't be dark all by myself. I want you white guys back here. We got to be complete, one of each. All right, here it goes again. Just nothing but flames, nothing but flames. And then the explosion comes when the dark particles hit. Boom. And now watch, it comes back. That's the only possibility that I can see. And the black particles are gravity. Okay, I am going to guide you through this explosion. Here it goes, and I'm going to turn it down to 25%. So that we can see it really slow motion. Already? So here we go. This is from atomcentral.com. And I'm going to probably turn the sound down. Alright, here we go. I'm going to turn the sound right off. The first thing that just happened here is this enormous glow. So what have we actually happened from the atomic bomb? The atomic bomb was sitting on the runway, just sitting there just all by itself, doing nothing in a little ball. And then it is just a ton of excessive electrons, and they just don't want to be next to each other. They hate each other. So it is called enriched plutonium, uranium, and it's got so many extra electrons in it, it can't handle them, and they want to get the hell out of town, and they do. And the way they do it is they have them in a confinement, and then they explode into it to force everybody's fields into each other's fields, and then they can't handle it. They just go flying, and all the whites go flying out, and they precede the blacks. So here's what happens. At this point right now, it just exploded. Forget this part. That part's gone now. Here we are now. The nucleus stays just where it was. It doesn't care. It's dark matter. It's just sitting there. It's happy being there all by itself. But it wants to have the white ones. The white ones just all took off because they were the ones that coated the black. So they take off. Now, what happens next? This is where we are now. The white ones are heading out, and they are hitting this building. And they are making it glow like a torch. Now, it's not moving. It didn't break. Nothing here broke. Nothing moved. Not a single thing moved. Zero. Understand? This is critical to understand, because the only thing that hit them so far was the outside white particles. The dark ones are the heavy mass. This is how we can understand what are the masses here. What is going on? The black ones have no glow to them. They don't make anything burn. They just push stuff out of the way. The white ones just burn things. They don't push anything. So here we are with the white ones. They're just starting to impact. Well, they have so many white ones flooding in here, it cannot absorb anymore, and that's what starts it to burn. And watch it burn so slowly. Now, again, I'm at 25% speed, so it would go 4 times as fast, but here it goes. Now watch. Look at it combust. This didn't go flying. Not a damn thing happened to it. Zero. It's just absorbed so many electrons that it's combusting. Watch. Boom, just like that. Now almost everything is burnt. Literally almost every electron is removed. Everything is scorched. But it did not fall over. Not a damn thing pushed it. Now, what happens next? Alright, at this point, we've burnt everything away. Now, what's going to happen next? The next part of it is the black and the white together, which is this. So now we'll forget all this stuff. That's gone. Alright? So now we're here, and the black's sitting all by itself way back where the bomb went off. The whites have already burnt all of the building away. I've burnt all the easy stuff. Now comes the black and the whites, because they will be tagged together, and they are the ones that hit right now, and everything goes. So, what will happen then? The black does not want to be all by itself. It says, hey, you guys, where are you going? And they said, well, you just blew us out of here. And they said, yeah, but I can't stay here by myself. Come on. So they all come back. That's not the nature of a bomb blast. A bomb blast goes out and stays out. this comes back. And just observe. Just keep your eyes on the prize. Here comes the heavy-duty stuff. Wham! Look at that. Absolute devastation. But no more burning. You see it? It's just a push. Now what happens? It's going to come back. You see? Now watch. Watch all of the dust and everything starting to come back. And pieces of it and all that. Okay, so you saw the house burn, then you saw the house explode. Well, what happened was these are the particles that originally hit the house and burned it. These are the particles that came next and knocked the house down. Cornell and some other ones were calling these 2P, 2H. 2P, which is particles, 2H, which is holes. That's what they are. Now they're calling them excitons. Muons. These are supposed to be muons. These are supposed to be neutrinos. They got so many names. Bosons, quarks, tetraquarks. I mean, it goes on and on and on. And every time I see something now, every day, well, we just discovered this. We just discovered this. We just discovered that. Well, let me tell you what. Rod and I discovered this at least 6 years ago. And I did this 6 years ago. It's called Light is Dark Energy and Matter in the Vacuum of Space. That's a video I did 6 years ago, showing that light traveling from the sun to us is these particles, and the universe is saturated with these particles. They used to call them ether. Okay, so what's the takeaway from this? The sun is spitting out all of these particles, and they are exactly like this. When they come out of the sun, they have that white particle attached to a black particle. The black particle just never changes. It's a solid, just a solid bowling ball. This one can squish and crush and expand and everything. So when these particles coming out hit our atmosphere, who has exactly the same particles out there, they scrub, and they create heat. That's why it's 2,700 degrees way out here. Why is it 2,007 degrees here? 2,700. They say, it's because of carbon. Well, how does a carbon make 2,700 degrees? They say, it holds the heat down. No, it does not. It scrubs against every other particle out here. You rub your hands back and forth, and what do you feel? You feel heat. Exact same thing here, only we're scrubbing in one direction. If you had a long enough hand, you'd feel it. So the real takeaway is that the people we are relying on for our physics information have, to me, they literally have no idea what they're doing. Now, if the people at MIT or any of these people will discuss anything that I've presented, I've been presenting this for 6 years to all of them, and I went to the University of Geneva, and they were very impressed and said, wow, we'll follow you. I said, okay, you're going to follow me? And that was the last I heard of them. I've tried with everybody. Literally everybody. Don Lincoln from Fermilab, who is looking for the particles that I am showing you, the muons and electrons, he says, I will not spend 10 seconds to work with you because you're not peer-reviewed. I said, I don't care if I'm peer-reviewed or not. I'm showing the evidence. Plus, my IQ is much higher than yours. I'm absolutely certain. I am in the 100th percentile, my friends. So if Don Lincoln can come to me with evidence, he's just shown absolutely nothing ever other than doodles. And I'd like to see his IQ. All right, if he thinks he's so smart and he can just disregard everybody else that comes with evidence, that's disgraceful. The reason that I get upset about this is because they treat me like an idiot because I refused to pay for a piece of paper that said, I repeat what you tell me to say. And that's exactly what they do. They cannot think for themselves, not a single one of them anymore.